In this lecture, I am going to discuss on offset quadrature phase shift keying digital modulation. So in the last lecture, we have seen the disadvantage of QPSK. That is why we moved on to offset quadrature phase shift keying digital modulation scheme. So the specific disadvantage was we could easily have incoming bit pattern which takes us from succeeding bit pairs going from 1 1 to 0 0 or 0 1 to 1 1 0. For example, let us consider the following specific bit sequences. Let's say 1 0 0 1, then 1 0 0 1, then 0 0 1 1, like this. Now look at the specific pattern from 1 0 to 0 1, then again 1 0 to 0 1, 0 0 to 1 1. This incoming bit patterns are mapped like this. So this point is 1 1 and this point is 0 1 and this is 0 0 and this one is 1 0. Now 0 1 to 1 0, look at this. So this is 135 degree and this is 335 degree. So there is 180 degree phase transitions from 0 1 to 1 0. Similarly, if you move from 0 0 to 1 1, again there is 180 degree phase transitions in this QPSK scheme. So here we have the first pair as 1 0 and second pair as 0 1, and therefore we are going from this phase to this phase, which is 180 degree. So I might go from this point to this point also. Okay, so it is quite possible that at various stages in the waveform you will have 180 degree phase transitions. Okay, and these 180 degree phase transitions are undesirable, particularly when you are going to finally band limit this waveform. Such a 180 degree phase shift variations will cause the envelope of the signal to go through zero. So essentially you will get a non-zero non-uniform amplitude or non-constant envelope waveform after filtering. So whenever you have infinite bandwidth, then it will not create any problem, but in practice we may not have infinite bandwidth for a given communication system. Therefore we know that finally we are not going to have this rectangular pulses, and this 180 degree phase shift transitions really mean that you have go through an envelope variations which goes through the zeros. Okay, so it becomes zeros in between. The amplitude does not remain constant through after filtering. Now to offset the effect, this 180 degree phase transitions. Okay, let's see what we can do. Okay, so in the constellation diagram, if you look at again, in this constellation diagram I had represented this point as 1 1, this point as 0 1, and this point as 0 0, and this point as 1 0 0. Okay, now how did I generate this incoming bit pair of 1 1 or 1 0 or 0 1 and 0 0? I looked at the two successive bits coming in, say 1 0 1 1 0 0 1 1, like this. This is my incoming bit stream. Okay, you just wait 2 bit streams, and after that you decide, okay, if it is 1 0 0 and this 1 0 is, you map onto this point, and then again wait another 2 bit duration, and then if it is 1 1 and you map on this 1 1 to this this point. Okay, and after this mapping what you do, you then finally transmit the waveform. And in this case, if you notice, then for each mapping you have to wait for 2 bits. Okay, that is, look at what the bit pair was and then carry out this mapping. But the alternate way is, I could as well carry out this mapping as and when each bit is coming along, instead of waiting for 2 bits. So you wait, 1 bit comes, then you decide something and transmit. So that is the whole idea of this offset QPSK. Okay, So let's say the specific interval of TB seconds. So what you are going to do is you are going to do this mapping at the interval of, instead of 2 TB seconds, you are going to do this mapping at every TB seconds. Okay, so this is what we are going to in this offset QPSK. So therefore you decide which of the constellation points are need to be transmitted instead of waiting for 2 TB seconds. Therefore, I need not wait up to the second bit to come along and then decide. As and when each bit comes along, let it decide now what the next phase will be. So your choice on the constellation is decided by not looking at the complete bit pair first and then deciding, but it keeps on making a transitions every TB seconds. So you're still looking at two bits, but the transitions occurs at every TB seconds. So that's the whole idea of this process. Now let us see how these things are carried out. Let's say I have the incoming bit patterns. Let me take this as an example. Okay, let me take my input bit stream is 1001, and if you are try to draw the waveform, then 1 I can represent a positive pulse, then 0 let me represent a negative pulse, 0, then again 1. Okay, so this indicates 1, this is 0, this is 0, and this is 1, and so on and so forth. It goes like this. Let's say it goes. Okay, now what you do is you split this waveforms into two waveforms. Okay, so this is incoming bit stream, and this incoming bit stream you separate into two bit streams, even bit stream and odd bit stream. See, this is odd bit stream, and this also odd, and this guy is even, and this guy is even. Okay, so now you are going to split it into even and odd. Therefore, the point is every TB seconds we are going through a bit transition. So basically what we are doing is we are extending the bit duration, each bit duration from TB seconds to 2 TB seconds. That let us see how we are extending the bit duration. See, originally the bit duration is TB seconds. Now let me take odd bits again. So let me take this odd bits. So this is TB seconds. Let me extend from TB seconds to 2 TB seconds. Okay, and then look at the next odd bit. This is my first odd bit. This one is the first odd bit. First odd bit. Now let us look at the second odd bit. This is my second odd bit. Second odd bit. Now in the second odd bit it is 0, therefore I will maintain 0, but this let me extend another TB seconds. Okay, like this. So this is my odd bit stream. Now if you notice here, originally the duration was originally the duration was TB seconds. Now the duration was 2 TB seconds. So instead of TB, I am having 2 TB seconds. This is my odd bit stream. Now take the even bit stream. This is my first even bit. First even bit. Okay, this first even bit, where the first even bit starts here, it starts at this point. So let's say the previous bit was, maybe the diagram is not very clear. So let me delete this. Now, so it is 0 for one duration and extend another duration. Now it is extended 2 times, and this is my second odd bit, right? Second odd bit is 1. Therefore you extend 1 bit duration, then again 1 bit duration, then come down. So this is my even bit stream. So change is being made every TB seconds in the incoming bit stream, whereas change is being made every 2 TB seconds in the odd bit stream and even bit stream. Let me call this odd bit stream as I channel or I bit stream. Here I stands for in phase, and here even bit stream, here this is called a Q channel, and where Q stands for quadrature. So we need to look at 2 bits in an interval of 2 TB seconds, but the way we are doing is slightly different from what we were doing earlier. So essentially we are converting the 1 bit stream into 2 bit streams. Okay, that is the first one is I bit stream, in phase bit stream, and the second one is Q bit stream. Okay, so you can think of this process as follows. I am converting this this into 2 quadrature bit stream. One we are calling as I bit stream, and the other we are calling Q bit stream. So the rate of I bit stream is basically half the bit rate of the original incoming bit stream. Okay, originally the bit stream is TB, and here the bit rate is half of the the original bit stream. Okay, originally the data rate is TB, and here the data rate is 1 by 2 TB. Similarly, the rate of Q bit stream is half the bit rate of the incoming original bit stream. So I take alternate bits. So let's say the even numbered bits going into the Q channel, and odd numbered bits are going into the I channel. Okay, so therefore actually this is an important thing. Okay, what you will see is the transitions in the 2 bit streams are really offset with respect to each other by a bit interval of TB seconds. So the transitions are not occurring together. When you regard them as occurring together, that will lead to QPSK, but we are not considering that transitions occurs together. It is occurring independently. So now you look at this waveform. Maybe I'll redraw this waveform again, so that let me give clear picture. So 1 0 0, then 1 like this. This is my incoming bit stream 1 0 0 1, and in phase I channel you make 1. I'm sorry. You make I bit stream, then extend the duration, then second odd bit stream you make 0 like this. This is I channel, and then here you go to 0, stay 0, and another pulse second is 0. Then you look at this is 1, therefore in this you come to 1, then stay 1 pulse duration, then stay 1 pulse duration. This is Q channel. The same diagram I am drawing here to give more clarity. This is I channel. Now look at this waveform carefully. Right now what you will do is you look at what is happening at each of these points. So as you can see, in a particular bit interval of TB seconds, whichever you take, one of the bit will remain constant. See, you take this interval, you take any bit intervals. Okay, let me take the first bit interval. So the first bit interval is like this one. First bit interval. In the first bit interval, you see the 1 remains constant. Here also 1, and here also 1. There is no change in the I channel. But look at here, there is a bit transition. It is from 1 and it is going to 0. And whether it is changing or not, it depends on what you have here. Okay, so the change in the Q channel depends on what you have at this point. Therefore, you can only move from any point in the constellation to any other point in the constellation. That any other point is only the neighboring points. You cannot move arbitrarily. So what are the points? Suppose you are in this point, either you can go here or you can go here, but you cannot come here. The third quadrant is not possible because only one bit is changing. So now you have 1 in the I stream. Look at here, 1 in the I stream. Here there is 1 in the I stream. Okay, and is going to remain at 1 and Q channel may change or may not change. See here it is changing or does not changing, depends on what you have here in this point, the first bit of even in the first even bit, so not even first even bit. Therefore, no matter how it happens, whether it changes or not in the Q channel, only one bit is changing, and therefore if only one of the bit is changing, and you have the gray code mapping. See in this I have the gray code mapping. See this is 1 1 and this is 0 1 and this is 0 0 and this is 1 0. You move from one point constellation to the neighboring constellation, there is only one bit changing. This kind of mapping is called gray code mapping. Gray code mapping. So therefore if you move in this gray code mapping, then what happens, only one bit is going to change. So every TB seconds you are moving from any points in the constellation to any one of the neighboring points. That is the whole idea. So it is still a quadrature. Why is it quadrature? Because we still have at any time 4 possible phases. Say this is 45 degree and this is 135 degree, 225 and so on and so forth. So still you have 4 phases and it is called a quadrature. But the transitions are going to occur only maximum of by 90 degree by a mechanism of offsetting of the bit streams in the I and Q streams. So the bit streams in the I and Q streams are offset with respect to each other by a bit interval of half the symbol interval T or 2TB. Therefore every bit is therefore being extended to twice its duration. Originally the bit duration was TB, and once you convert into even bit or odd bit, the bit duration is extended to 2 TB durations. But the processing is done on symbol by symbol basis. That is, the symbol is 2 bits. The I stream is being modulated by, let's say, the in phase carrier, let's say cos 2 pi f naught t, and the Q stream is being modulated by sine of 2 pi f naught t. Okay, therefore now we are transmitting the signal continuously, but now the transitions will occur at every TB seconds. So in the QPSK the transitions were occurring every 2 TB seconds. So QPSK transitions occurs at every 2 TB seconds, but here in offset QPSK the transitions occur at every TB seconds, half the symbol duration. Therefore, what we have really done is we have traded off the points of transition which were earlier occurring at a slow rate. Now the transitions occurring at a fast rate more frequently, that is at every TB seconds. So earlier if you look at the transitions occur at this point, maybe let me read all the waveform again. This is like this. See, earlier the transitions occur at this point. This is one transition point and again another second transition in QPSK, right? So every 2 bit pair, this is 1 and this is 0. So after 1 0 there is one transition. Let's say this is one bit duration. Let's say this is 0. So 1 0 to 0 1. So only 2 transitions now. 2 transitions in QPSK. But if you take a offset QPSK, take the same waveform. Here one transition, let's say first transition, and here second transitions, and third transitions, and fourth transitions. So there are many transitions. Therefore, I'll go through many more transitions in offset QPSK. Okay, so that's the whole idea in this offset QPSK. In fact, in QPSK we had a 180 degree phase shift, okay, one that is 180 degree phase transitions, but in our new scheme we could only have 90 degrees phase transitions at the most. Okay, and these transitions will now occur at every bit interval basis rather than every pair of bit interval basis. This scheme of QPSK is called a offset QPSK. And in this offset QPSK, as I already told you, as I already said, the incoming bit stream is first split into two streams. So you have the incoming bit stream split into two streams. This is odd stream and this is even stream. And the odd stream you modulate by in phase carrier, where the in phase carrier is cos omega naught t, and here you modulate by quadrature carrier, where quadrature carrier we assumed sin omega naught t, and this is incoming bit stream. Let's say 1001, this is odd and this guy is odd. Okay, so therefore your odd contains 1 0 and this is even and this one is even, therefore even contains 0 1. That's it. So this scheme of QPSK is called offset QPSK. So the offset QPSK contains two quadrature carriers, right? And after this you do this modulation and then finally you do the addition, okay, added together, and this is called offset QPSK. The two pulses in the two channels are offset with respect to each other by the interval of 1 bit interval, that is half the symbol interval rather than 2 bit intervals. Okay, this is the whole idea of QPSK. Okay, so at this point I'll stop in this lecture, and the next lecture I'll talk about the mathematical representation of QPSK. So upcoming lecture we are going to discuss mathematical expression, or how do we represent mathematically the whole operation what I said now, mathematical expression for offset QPSK. That we will discuss in the next class. Thank you.